All right. So that was a lot of talk about hydrogen ion concentrations and hydroxide ion concentrations. And one thing I hope you realized is that they're kind of awful because they're pretty small. They're things like 1.0 times 10 to the negative 7 or 1.67 times 10 to the negative 14. And so what math, chemistry, whatever does is develops a shorthand. The shorthand for hydrogen ion concentration is pH, and the shorthand for hydroxide ion concentration is pOH. Now, for those of you who are taking Math 12 or have taken Math 12, this is a logarithmic relationship because my concentrations are all base 10. So if you look at these concentrations of hydrogen, and it's not like these are the only concentrations of hydrogen, these are just the ones that end up nicely. But we've got 1 times 10 to the negative 14, 1 times 10 to the negative 13, and so on. And if you look at the pHs, when the exponent is negative 14, the pH is 14. When the exponent is negative 13, the pH is 13. So it's this idea of solving for the exponent in a way. Log base 10 of 10 to the negative 13 would be negative 13, and then we just reverse the sign. So it's a logarithmic relationship that you don't have to understand or know. We're just going to teach you the math to do. But what I want to just sort of emphasize is this shorthand. Now, these are all written as 1 times 10 to the, so it's going to appear like when you're finding concentration, you can just take the negative of the exponent. It's not true, but for these ones you can, right? Because it's 1 times. So what I want to look at is just simply when you have a concentration of 1 times 10 to the negative 6 as a hydrogen ion concentration, the pH is 6. When you have a concentration of 1 times 10 to the negative 4, the pH is 4. The math is going to get more complicated, but this is just nice and simple. What I want to look at is what this means. When you have a pH of 4, that is more acidic than a pH of 6. How many times more acidic is it? You'd have to use the concentrations to figure that out. pH is a shorthand. Concentration is your longhand. It's kind of like percent in a way, right? One has a mathematical value and one you have to change into a mathematical value. So if I take these and I plug them into my calculator, 1 times 10 to the, or 1 exp, or EE, negative 4, divided by 1 times 10 to the negative 6, you get 100 as an answer. A pH of 4 is 100 times more acidic than a pH of 6. And that's just something you'll know. Anything base 10, we use base 10s for earthquakes, right? So an earthquake of a magnitude 4 or 6, actually it's reversed, but anyway, a magnitude 6 earthquake is 100 times more stronger than a magnitude 4 earthquake, right? And then I also want to look at the relationship between all the concentrations and pOH and pOH. So we've been focusing here on just pH, but let's try to look at it all. So let's take one line on this chart. Okay, let's take the line of a pH of 6. Here we go. When you have a pH of 6, the hydrogen ion concentration is 1 times 10 to the negative 6 moles per liter, or molar. The hydroxide ion concentration is 1 times 10 to the negative 8. The pH is 6, and then the pOH, which we haven't talked a lot about yet, is 8. Now what we want to do is look at the relationship between these values. We've already been talking about the value of Kw. Kw is equal to the concentration of, I was about to write hydroxide first, but we always do hydrogen first. It doesn't matter. Hydronium, or hydrogen ions, times the concentration of hydroxide. If you multiply these two together, you'll notice you get that 1.0, which I'm not allowed to write that many sig figs if I was actually multiplying together. So 1 times 10 to the negative 14. No units on Kw. Well, what about pH and pOH? If the concentrations multiply to give me 1 times 10 to the negative 14, then what I want you to just start realizing is that the pH and the pOH are going to add to give me 14. Again, if you've taken a bunch of math, this makes mathematical sense, but I just want you to know these two relationships. In a substance at 25 degrees Celsius, the product of the hydrogen and the hydroxide will always be 1.00 or 1 times 10 to the negative 14, and the pH and the pOH will always add to 14. So if we look anywhere on this scale, when we have a pH of 13, we have a pOH of 1. When we have a pH of 4, we have a pOH of 10. They always add to 14 because their concentrations will always multiply to give 1 times 10 to the negative 14. Okay, so that's one thing. The other thing I want to look at is the acid-base scale. Actually, I think I've got that in here down here. So things to note. As you're looking at this scale, when you're talking about pH, pH generally runs from 0 to 14, and it's 0 down here all the way up to 14 up here. Whereas the pOH scale starts with 14 down here and goes down to 0 up here. So if I was asking you how these pH scales work, you'd say as the pH scale increases, the pOH scale decreases because they always have to balance out to add to 14. Okay, now let's talk about relative acidity and basicity. When you look at the scale, a pH of 0 is very acidic, whereas a pH of 14 is basic. So if you have a pH that is less than 7, your solution is considered acidic. And if your pH is greater than 7, your solution is considered basic. At 7, we call this neutral, because at a pH of 7, you would also have a pOH of 7, so they add to 14, so they are equal, and your substance would be neutral. But what about pOH? So if the pH is less than 7, something here, that's acidic. But when your pH is less than 7, your pOH is greater than 7. So it's reversed. A pOH greater than 7 is acidic, whereas a pOH less than 7 is basic. It's a little bit confusing. We're more comfortable with pH than we are pOH, and that's okay. But it's just something to start looking at. The other thing to look at is looking at the concentrations. It's sometimes hard to tell what numbers are bigger than others. So a 1 times 10 to the negative 14 concentration is small versus a 1 times 10 to the 1 concentration is large. As your hydrogen ion concentration increases, you get more acidic, but your pH is decreasing. So when your concentration of hydrogen ions is 1 times 10 to the negative 14, your pH is 14, which is quite basic, right? Whereas when you go up here to something like 1 times 10 to the negative 2, you have more hydrogen ions in solution, but your pH is smaller. So to generalize that, as the hydronium or hydrogen ion concentration increases, the pH value decreases and it becomes more acidic. So more hydronium, lower pH, more acidic. Whereas with hydroxide, as the hydroxide ions increase, so this is a very low concentration of hydroxide, very acidic. This is a very high concentration of hydroxide. The same thing happens with the pOH scale. So a pOH of 14 is acidic, just like a pH of 14 is basic, right? Whereas when you have a lot of hydroxide, you actually have a low pOH, and it's going to be basic. So as your hydroxide ion concentration increases, your pOH value also decreases, which is why low pOH is basic, low pH is acidic. Hopefully that makes sense. And then just one more little side note is that this range goes from 0 to 14. This is typical for dilute aqueous solutions, but it is possible to get pH or pOH values outside of this range for very concentrated acids and bases. In fact, you can even get negative pH values, which kind of blew my mind. All right, go and learn.